This is actually a walkthrough for your thermal energy unit test. This is your scoring sheet. You can access this. I'll give you a paper copy so you can write on it, but then you can access the digital copy through Canvas. That way you can click on each of these links and go to the 3 different sections of your test. So it's broken down by learning targets. So part 1, if you notice, it's the exact same setup as your your project, right? So part 1 was all about the states of matter and then physical and chemical changes. So we're going to do that part first. Part 2 will be the types of heat transfer, convection, conduction, radiation, and part 3 is your insulator and conductor. So that's like your material, the mass, and its effect on thermal energy. So each section is worth a few different points off to the side based on how much you receive in points. That'll show mastery in progress or getting started for those specific skills. Okay. Here we go. Part 1. So obviously click in your full name here. Last initial is fine if there's no other person with that same name in 6th grade. All right. So on the first question, what is thermal energy? Is it the average amount of energy in the molecules, or is it the total amount of energy? So if I look at an object, am I just going to take all the energy, divide it by however many molecules there are, or am I going to count up all of the energy total in all the molecules? So thermal energy, which one's that? Average or total? The next one, which of these objects, a hot cup of coffee or a huge frozen iceberg, which one has the most thermal energy? The hot cup of coffee or the frozen iceberg? What is temperature? Is temperature the average amount of energy that an object has, or the total amount of energy that an object has? So when you stick a thermometer in your mouth, right, or you scan your forehead now, I guess is what you usually do, are you taking the average amount of energy in your entire body, or are you totaling up the amount of energy of all your molecules? The next one, which of these objects, glacier, ice cube, the sun, and a boiling pot of water, which of them has the highest temperature? Iceberg, ice cube, sun, or boiling pot of water? Highest temperature. Molecules. Molecules have kinetic energy because they are always doing what? Molecules are always exploding. Molecules are always motionless. They don't move. Or molecules are always vibrating. How does thermal energy transfer? So how does thermal energy go from one object to another? Does it go from cold to hot? From hot to cold? From big to small objects? From small to big objects? Or does it only go between magic potatoes? Why is there more thermal energy in an iceberg than in a pot of boiling water? Why is there more thermal energy in an iceberg than in a pot of boiling water? The pot insulates the heated molecules. Most icebergs are fairly warm to the touch. Icebergs contain many more molecules than pots of water, or water does not hold heat very well. So what's the reasoning behind an iceberg having more thermal energy? Because the pot insulates the water. Most icebergs are fairly warm. Icebergs contain many more molecules than that pot of water, or water does not hold heat very well. As molecules move faster in a material, so the molecules start moving fast, 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 fast. Thermal energy does what? And what does temperature do? Okay, so the molecules are moving faster. Does the thermal energy increase and the temperature decrease? As the molecules move faster, does the thermal energy decrease and temperature increases? If the molecules start moving faster, does that mean that the thermal energy increases and the temperature increases? Or thermal energy and temperature have no relationship whatsoever? This image shows water being heated in a pot over a campfire. What's happening to the molecules of water in the pot. So what's going on with the molecules? The molecule's motion decreases, and this increases its kinetic energy. The molecule's motion increases, increasing kinetic energy. The molecule's motion decreases, decreasing kinetic energy, or the molecule's motion increases, decreasing kinetic energy. Which picture shows the molecular structure of water molecules? So which one of these is the molecular structure of water molecules, or at least a cartoon representation of it? The diagram below shows an arrangement of particles. You could also say molecules. We say that a lot in class, okay? Does this look like a solid, a liquid, or a gas? Or does it look like a gumball machine? Liquid molecules are tightly packed. Liquid molecules are loosely bonded and flowing. Liquid molecules are free to fly in all directions. Liquid molecules are yummy, all over ice cream. Which state of matter has particles that are very far apart from one another? Is that a solid, a liquid, or a gas? If those particles or molecules are really far apart from one another, is that a solid, a liquid, or a gas? All right, here's a picture of boiling water. Boiling water, is that a physical change or a chemical change? Here's a picture of rusty nails. Okay, so when the nails rusted, is that a physical change or chemical change? Here are fireworks exploding. Is that a physical change or a chemical change? And water freezing. Is that a physical change or a chemical change? A change that alters the form or appearance of a material, but does not make the material into a new substance. What does that mean? Is it a physical change or a chemical change? It does not create something new. It just simply changes the appearance. What is the definition of a chemical change? A change that creates a brand new product, or a change that only affects the appearance of a product? What's the definition of a chemical change? Yay, you're finished with part 1. So when you hit submit, it's going to give you your score. That's when you're going to go back and record it right here for part 1. So how many points did you get out of 20? And then that will determine if you are mastery, in progress, or getting started. So you fill out your points here and you can circle mastery, in progress, or getting started. And then click on part 2. We're moving on to convection, conduction, and radiation. So part 2, again, put your name, right? The transfer of thermal energy from one object to another is called what? So when that energy goes from one object to another, is that heat, temperature, radiation, or potential? What do you call that? Blank is the type of thermal energy transfer that causes a campfire to warm us. So if you notice, right, heat going to the hand, is that convection, conduction, radiation, or s'mores? The sun shines down on this family as they play on the beach. Is that convection, conduction, or radiation? The sun shining down on them. Walking on the warm sand with your bare feet. Which one is that? Convection, conduction, or radiation? When you're actually walking on the sand. Warm air rises and cool air sinks to the ground. Whee, right? This whole process is this convection, conduction, or radiation. Baby chickens, they're kept warm from heat lamps, right? Some of you guys had heat lamps in your food trucks, right? So are those heat lamps convection, conduction, or radiation? When you open the refrigerator door at your house, right? If you keep it open for a little bit, what's going to happen? Thermal energy in the refrigerator is going to be transferred to the air outside, Or is thermal energy from the air outside of the fridge being transferred into your refrigerator? So which way is the energy going? Is energy coming out of the fridge? That's what this one is, right? Energy is coming out of the fridge into the air around you in your home. Or is energy going into your fridge? That's what this one is. Okay. Energy comes out of the fridge, energy goes into the fridge. In some cultures, walking on fire is the ultimate sign of strength. What type of thermal energy transfer is this? You are literally walking on hot coals. Is that convection, conduction, or radiation? And warm air from this heater creates a current, a circular pattern, right? So when the warm air rises, it causes cold air to sink back down. It's always pushing, right? Because when the warm air rises, it pushes the cooler air down. Okay? Cooler air sinks. It is more dense. Is that convection, conduction, or radiation? Exact same thing here, guys. This is a lava lamp. So when the light bulb is heating the wax will rise, right? It gets hot. It's less dense. It's going to rise up. When it gets to the top, it cools off and becomes more dense and sinks back down. So there's a whole circulation pattern here. Is that convection, conduction, or radiation? All right, here's the scenario, right? You got 2 cups of coffee. One is hot, one is cold. All right. You place 1 cup of near freezing cold water and 1 cup of hot water in a room temperature room. Okay. So it's just like we put it here in the classroom. Okay. Which cup will transfer thermal energy to the air surrounding it? So pretend I just walked into our classroom and I set these 2 down in front of you. Which one is going to transfer energy to our classroom, to the air in our classroom? Is it going to be the hot cup or the cold cup? Okay, click those. Which cup will absorb thermal energy from our classroom? So it's going to take energy from our classroom air and absorb it. Is that going to be the hot cup or the cold cup? Miss Newald, me. I place a metal spoon in a container of hot water with the temperature of 120 degrees Fahrenheit. Okay. After 5 minutes, I measure the temperature of the spoon in the water. Okay. So the water was super hot. I put the spoon in. Okay. When I measure the temperature of the spoon's 97 degrees Fahrenheit. Which statement best describes the flow of energy between that super hot water and the spoon? Here are 3 options. The thermal energy transferred from the spoon to the water, heating the spoon and cooling the water. The thermal energy transferred from the hot water to the spoon, heating the spoon and cooling the water. Or thermal energy transferred from the hot water to the spoon, heating the spoon while the water temperature stays the same. So what's going to happen? Okay. Is there going to be a heat transfer from the spoon to the water? Is there going to be a heat transfer from the water to the spoon, causing the spoon to get hot and the water to get cooler? Or is it going to go from the water to the spoon, causing the spoon to get hot and the water temperature stays the same? All right. Which type of heat transfer took place between the spoon and the water, right? So I put the spoon in the water. Is that convection, conduction, radiation, or chemical? What type of heat transfer is that? Yay, you're finished with part 2. Okay, so you're going to hit the submit button and record your score right here. So how many points did you get out of 14? That's going to determine mastery, in progress, or getting started. Go ahead and circle your score. And then you can click on the final part, part 3, which is all about your insulators and conductors. So again, put your name, right? First question, materials that allow heat and electricity to move easily through them are called what? Insulators or conductors? Heat and electricity can move easily through them. Materials that resist the flow of heat or thermal energy are called what? Okay, so they slow down or try to stop thermal energy from being transferred. Is that an insulator or a conductor? Now you have three pictures, right? A metal pot, a paper clip, and aluminum foil. Are these examples of insulators or conductors? Now you guys have three pictures, right? You have oven mitts. You have that little, I don't know, poofy thing that your to-go pizza comes in, if you've ever seen them like slide that out from Pizza Hut. And then you have plastic straws. Are those insulators or conductors? Now you have multiple pictures here. These are kind of funky, right? So this is actually like copper wiring. This is an oven mitt. This is some kind of a metal pan that you would cook with and a metal spoon. Okay, so select the one insulator. Out of these four objects, which one is the insulator? The copper wire, the oven mitt, the frying pan, or the metal spoon? Objects with more mass have more molecules and less potential energy. More mass, more molecules equals fewer molecules. More mass, more molecules, and more thermal energy. Objects with more mass have more molecules and higher temperatures. So if something has more mass and more molecules, does that automatically make them hotter? If something has more mass and more molecules, does that automatically give them more thermal energy? All right. Here are two pictures. You have a golf ball and a ping pong ball. I don't know if you've ever held one. Ping pong balls are very light and hollow, and your golf ball, much heavier, much more dense, right? Okay, so a golf ball and a ping pong ball were left outside during the summer. Notice they are the same temperature, okay? So it's in Celsius, but at least you know that they're the same, right? So both of them measure 27 degrees Celsius, right? They're the same temperature. The golf ball has a much higher mass, right? It's 47 grams. If we put that on our teeny tiny scale in the classroom, it would weigh 47 grams. Okay. Most measurements that you guys took for like your zombie hand warmer was like what, like 3 or 4 grams, something like that. Maybe 10 was like outrageous. So that gives you an idea. Okay. The mass of the ping pong ball is only 2.7 grams. So totally different mass. Okay. So does the golf ball or the ping pong ball have more thermal energy? They're the same temperature. Which one has more thermal energy? Thermal insulators are materials that do what? So insulators, what do? Do they allow the transfer of heat quickly? Do insulators allow the transfer of cold quickly? Or do insulators stop or slow down the transfer of heat? Thermal conductors are materials that do what? Conductors allow heat to pass through. Typo, sorry. Conductors are materials that allow cold to pass through. Conductors are materials that stop heat from passing through. Conductors are materials that stop cold from passing through. So what would you say a conductor does? Bike tires are an example of what? An insulator or a conductor? And you are finished with part 3. Congratulations. You are completely finished with your testing over thermal energy. Hit your submit button, and you guys are going to record your overall score out of 13 points. That will tell you if you are in mastery, in progress, or getting started range. This is the important part here, okay? So when you're finished, you have this written down on a paper copy. That is what you want to take a picture of, okay? And you're going to upload it to Empower. There is only going to be one thing in science for thermal energy, and it is your mastery unit test for thermal energy. So that's where you're going to upload it. If you get stuck, You can wait to upload it. Just please take a picture of it so you at least have the picture before you turn it in to the science tray. So again, if you can find it, please upload a picture of it to Empower, not Canvas, Empower. If you go on Empower and you can't figure it out, please don't disrupt the rest of the learning that's going on. Just wait, take a picture of it, and turn it into the science tray. We'll all upload it later when you need more guidance. Okay? Thank you so much.